Let us start by making a very important point about isogenies. So the way we have defined isogenies, we are saying that the isogeny takes the special point of elliptic curve E1 to special point of elliptic curve E2. Now just this simple property will induce a group homomorphism. So this isogeny will act as a group homomorphism. It takes the group living on E1, which we defined by the chord tangent method, to the group living on E2. So you have a group homomorphism over the closure of the defined field K. So this is closure and this is K. So just by taking the special point O1 to O2, we get a group homomorphism. So every time when we think about isogeny, we are thinking in terms of group homomorphism of two elliptic curves. So you're saying isogeny from E1 to E2, you're essentially thinking in terms of group homomorphism, which preserves the special point. So we have to show this, that this isogeny, the way we have defined it, will induce group homomorphism. So we have to show this. But in order to check an isogeny, by our definition, we just have to check whether the special point of E1 is carried on to special point of E2. So this we will do at the end of the lecture, but now we will discuss a standard form of isogenies. So standard form for isogenies. So say we have this short Weierstrass form of the elliptic curve given to us as this: y square is equal to x cube plus ax plus b, and you have an isogeny which takes curve E1 to E2. So E1 is in this short Weierstrass form and E2 is also in this short Weierstrass form. Then our isogeny has a very simple form. You can write it as fractions px over qx for the first coordinate and sx by tx times y, the second coordinate. So this very simple fractional form there is. Obviously we will also say that p and q are co-prime and s and t are co-prime. So notice that isogeny, if you're giving it, it should be in the form of r1 xy and r2 xy. So the first function should also have some y in it, second function should also have y in it. So it is given as rational function of xy and rational function of xy. So where this is a rational function, and these rational functions are of the form like this. There's a polynomial in the numerator and polynomial in the denominator. It obviously has both x and y, so you can think of it, the coefficients are in x and the polynomial is in y. So you can write it like this. So numerator goes till n1 terms and the denominator, so b0 b1 goes till n2 terms. So just two polynomials, both are in x and y, and we are just arranging them. Now this is the general form. So this r1 and r2 actually look something like this. So we are going to go from here, this general form, which should be the rational function, to something really simple, which is this form. So just because our curve is given like this in a short Weierstrass form, you can form a simple standard form of isogeny like this. So let us see how this happens. So obviously we are given an elliptic curve like this. Y square is something like f of x. So if y square is of the form f of x, then wherever you see y square, you start plugging in f of x. So for an even n is 2k, you can replace this y to the power of 2k with fx to the power of 2k. So every even term here is replaced. So you replace every even term with fx 2k. So all the even terms are just functions of x. So even terms are in x. So what if y is odd? So if n is 2k plus 1, the power of y is odd, then you retain the even power f as this fx to the power of 2k, and for the odd you just multiply with y. So for the odd powers you just have multiplication by y. So this entire fraction here for both r1 and r2 will reduce something like this: f1x, f2y, f3x, f4y. So all the even terms are coming here and all the odd terms are coming right here. Now you multiply the numerator and denominator by, say, f3 minus f4y. f4 times y is just the conjugate of this. So put a minus sign here. And obviously now in the denominator you will get f3 square minus f4 square y square. So when you multiply by this, both the numerator and the denominator, so multiply the numerator by f3 minus f4y and the denominator by f3 minus f4y. In the denominator you will get a y square term, and you are going to replace that y square term with f of x. So this will simplify to something like this: g3x, g1x, g2xy. So as we mentioned before, the isogeny is a group homomorphism, and we already know that the inverse of a point xy is x minus y. This we have seen before, the way we constructed the group law. So since phi is an isogeny, it's a group homomorphism. So if you take this apply isogeny to inverse of a point, so it is negative of the original point. So that is a property of group homomorphism. This is inverse, so you put a negative sign over this part. So now how does this look like? So this phi of x comma minus y, so this you just take this form here. Instead of y you plug in minus y, so we get this. Now minus phi of xy, you have to take negative of this, but negative of this is just the first coordinate remains the same. First coordinate remains the same. The second coordinate you put a negative, so negative of a inverse of a point is just this. So second coordinate you copy as such and you put a negative. So we have this equality here. So let us first consider this. Set this equal to this. So first coordinate is equal to first coordinate. So if you set these two coordinates equal to each other, that will give g of 2 as 0. This is kind of obvious. You plug this thing here, you get g1 minus g2y divided by g3. So this is the first part, and the second part is just as such. So that is g1 plus g2y over g3. Now you solve this, everything will cancel out, and this obviously will give you 2g2y is equal to 0. That would imply g2 is 0, because obviously y is a variable. Similarly for the second part, equate these two. Now since we have taken this for r1, so r2 has to be a different fraction. So you, instead of g1, g2, g3, you can write m1, m2, m3, but that does not really matter. It's just change. So let us do this. So if you plug this in, this is again of the same form. You have g1 minus g2y divided by g3, but now you're saying negative of this. So negative of this would be, you get minus g1 minus g2y over g3. So g3 cancel out, and then you have this cancels out, so 2g1 is 0. So g1 is 0. So you equate the second ones, you get g1 as 0. So we have been able to get our result. You know, if the g2 is 0, that means multiplication by y is 0. So this term completely goes away. You have g1 over g3, cancel any common factors, you get p over q. Now in the second case, g1 is 0, you get g2 over g3. So this y goes right here, cancel any common factors, you get s over t. So we have been able to express numerator and denominator as relatively prime, and this is the form we get. This is called the standard form for isogeny. So you can see the first fraction is just only in terms of x, and the second fraction is again in terms of x, but you multiply it with y. Now we come to our this first thing which I promised you, that this isogeny, taking special point of elliptic curve E1 to special point of elliptic curve E2, will induce a group homomorphism. And this essentially comes from Riemann-Roch, because the special point plays a special role in constructing the isomorphism from the elliptic curve to the Pick group. So notice that this is this phi star is the divisor taking from E1 to divisor of E2, and we have talked about these divisors and the Pick group in our lectures on Riemann-Roch. So basically, what does this divisor of E1 look like? It's just a formal sum like this: np, p. To every point you're attaching a number here, and this gets attached to np and then phi of p, whatever this isogeny will take this point p2. And when you modulo out your principal divisors or degree 0 divisors, you will get the Pick 0 groups. So from here you modulo out your principal divisors, you get Pick 0 group. Same map here comes down here. So because you just modulo out the principal divisors. Now you can construct this map from E1 to Pick 0 E1. This we constructed in the lectures on Riemann-Roch. So this is an isomorphism. You take a point P and you map it to again Pick 0 P minus the special point. Similarly, you have an isomorphism here where you take a point of elliptic curve E2 and map it to P minus O2. So this is mapping to pic 0. So we have shown this mapping in lectures on Riemann rock. So this is the standard, so this is a homomorphism between divisor groups. So this homomorphism carries here, and so this is a homomorphism. So these are groups, these are naturally groups which inherit their structure from divisors. And yeah, so this is a homomorphism. So this is iso, this is iso, this figure is commutative, this is homomorphism. So this entire thing implies that this is also a homomorphism. So that's how we get. So just by this special points, mapping of special points, we were able to get homomorphism. And you know that this thing works precisely because of the structure of this pic 0 group, because the way we constructed the isomorphism between elliptic curve and pic 0 group, that is what induces the homomorphism. So again, you can find this on in the playlist Riemann rock. So now we end this lecture with a remark. So isogeny is actually an equivalence relation. So you have reflexivity because of ID being isogeny, and you have transitivity because composition of isogenies. You take any isogenies, compose them, you will still get an isogeny.